Right now, as you lie here, you are moving. Not just the ordinary motion of a body breathing, a heart beating, blood circulating through its quiet channels. Not even the motion of the Earth rotating beneath you at roughly 1,600 kilometers per hour, or the Earth orbiting the Sun at about 107,000 kilometers per hour. You are moving in ways that have nothing to do with any of that. The entire solar system, the Sun, all 8 planets, every moon, every asteroid, every comet, is orbiting the center of the Milky Way galaxy at approximately 720,000 kilometers per hour. One full orbit takes roughly 230 million years. The last time our solar system was in this position in its orbit around the galactic center, the dinosaurs did not yet exist. The dominant animals on Earth were small reptiles no one has named, living in a world that would be unrecognizable. And the Milky Way itself, the entire galaxy, all 400 billion stars, all the gas and dust and dark matter, is hurtling through space toward a point in the constellation Centaurus at roughly 2.2 million kilometers per hour. Not because something pushed us, because something is pulling us. Something we cannot see, something we cannot fully explain. Something so massive that it reaches across hundreds of millions of light years of space and drags entire galaxies, tens of thousands of them, through the universe toward a single point, like leaves circling a drain in slow motion on a cosmic scale. Scientists have known about it for nearly 50 years. They have named it. They have mapped around it. They have built entire frameworks of cosmological theory attempting to describe what it is and why it exists. And they will tell you, if you ask them carefully enough, that they do not entirely understand it. They never have. This is the story of the Great Attractor. You need to understand something about how space works before this story makes any sense. When most people picture the universe, they picture galaxies scattered more or less randomly through an infinite dark space, separated by unimaginable distances, each going about its own business, drifting slowly in whatever direction the Big Bang originally sent them. This picture is wrong. Not slightly wrong. Fundamentally wrong in a way that changes everything. Galaxies are not scattered randomly. They are not independent. They are not drifting freely. The universe has structure. Enormous, intricate, ancient structure, built by gravity over 13.8 billion years into a pattern so vast that it can only be seen when you zoom out far enough to make entire galaxy clusters look like dots. That structure is called the cosmic web, and it is one of the most beautiful and terrifying things science has ever revealed. Imagine taking every galaxy in the observable universe, somewhere between 1 and 2 trillion of them, and mapping their positions in 3-dimensional space. What you would see if you could step outside the universe and look at it from a distance is not a uniform fog, not a random scatter. What you would see is a web, vast filaments, each hundreds of millions of light years long, made of galaxy clusters strung like beads along threads of dark matter. Sheets of galaxies spanning unimaginable distances, and between them voids, enormous, almost perfectly empty spheres of space, hundreds of millions of light years across, containing almost nothing. Not darkness exactly, because there is no light to make darkness visible. Just space. Pure, cold, nearly structureless space. This is what the universe actually looks like on its largest scales. And within this web, nothing is still. Everything flows. Every galaxy, every cluster, every filament of matter is moving, pulled and pushed by the gravitational influence of everything else. The universe is not static. It is dynamic, alive in a gravitational sense, constantly rearranging itself in slow motion toward configurations it will never quite reach before the accelerating expansion of space changes the rules again. Understanding this, really feeling it in the way it deserves to be felt, is the foundation of everything that follows. The story of the Great Attractor begins in the late 1970s, and it begins with a problem. Astronomers at the time were building the first large-scale surveys of galaxy motions. Not just where galaxies were, but how fast they were moving and in what direction. By measuring the Doppler shift of light from distant galaxies, the way light stretches to redder wavelengths when a source moves away from you and compresses to bluer wavelengths when it moves toward you, they could measure velocities. They could build maps of cosmic motion, and what those maps showed was disturbing. If you removed the component of galactic motion that came from the overall expansion of the universe, the general drift apart of everything from everything else that has been happening since the Big Bang, you were left with what astronomers call peculiar velocities, the component of a galaxy's motion that cannot be explained by the universe's expansion alone, the component that must be caused by local gravity. In a perfectly uniform universe, these peculiar velocities would be small and random. Galaxies would drift this way and that, tugged by the gravity of their nearest neighbors, but there would be no systematic pattern, no large-scale flow. What the astronomers found instead was that our galaxy, and hundreds of other galaxies around us, all had peculiar velocities pointing in the same direction, all flowing, systematically, toward a region of sky in the direction of the constellation Centaurus. The velocities were enormous, hundreds of kilometers per second, far too large to be explained by any known gravitational structure in the neighborhood. The nearest large concentrations of matter, the Virgo cluster, the largest nearby cluster of galaxies, could account for some of the motion but nowhere near all of it. Something else was out there, something massive, something hidden. A group of astronomers known informally as the Seven Samurai, Alan Dressler, David Burstein, Roger Davies, Sandra Faber, Donald Lynden-Bell, Roberto Turlevich, and Gary Wegner, published the systematic analysis of this motion in 1988. They were the ones who coined the term, the Great Attractor. It was not meant to be poetic. It was meant to be descriptive, something great in scale, something attracting, something whose nature, at the time of naming, was entirely unknown. Here is what made the Great Attractor so profoundly frustrating to study. It was hiding, not deliberately, of course, not in any meaningful sense. But the region of sky toward which all those galaxies were flowing happened to be almost perfectly aligned with the plane of the Milky Way, the dense band of stars, gas, and dust that constitutes the disk of our own galaxy. Looking through the plane of the Milky Way is like trying to see something on the other side of a room full of fog. The dust absorbs light. The stars crowd the field of view and make it nearly impossible to identify distant background galaxies against the noise. Radio waves and infrared light can partially penetrate where visible light cannot, but even these have their limits. Astronomers called this region the zone of avoidance, a belt across the sky, roughly 20 degrees wide, centered on the galactic plane, where the Milky Way's own body blocked the view of whatever lay beyond. And the Great Attractor sat almost perfectly within this zone. For years, astronomers argued about what it could be. Some thought it was a single enormous concentration of mass, a supercluster of galaxies so dense and massive that its gravity reached across hundreds of millions of light years and shaped the flow of everything around it. Others thought it might be something more diffuse, a broad region of elevated density rather than a single point. What everyone agreed on was that it was there, it was massive, and they could not see it. The mass implied by the peculiar velocities was staggering. Estimates put it at something like 10,000 trillion times the mass of the Sun, 10 to the power of 16 solar masses. A concentration of matter so enormous it was difficult to express in any unit that felt intuitive. For a decade, it remained a gravitational ghost, known to exist by its effects, invisible. Then slowly the tools got better. In the 1990s and early 2000s, radio telescopes and infrared observatories began to see through the zone of avoidance in ways that were not previously possible. Surveys using these wavelengths started revealing what was hidden behind the Milky Way's curtain of dust. What they found was not a single, discrete object, not one enormous galaxy or cluster sitting there like a cosmic anchor. What they found was a region, a complex, tangled region of mass concentrations. Multiple galaxy clusters, overlapping and interacting, their combined gravity creating the enormous pull that the peculiar velocity surveys had detected. The most significant of these was the Norma cluster, a rich, dense cluster of galaxies sitting almost exactly at the position astronomers had predicted for the Great Attractor center, hidden almost perfectly behind the galactic plane. When radio and X-ray surveys finally revealed it clearly, it was exactly where the mathematics said it should be. But it was not enough. The Norma cluster was massive and real and important, but its mass alone could not account for everything. The peculiar velocities were too large. The flow was too systematic. Something more was contributing, and it was coming from even further away. Here is where the story takes its first enormous leap outward. Because in 2014, a team of astronomers led by Brent Tully at the University of Hawaii published a paper in the journal Nature that redrew the map of our cosmic neighborhood in a way that fundamentally changed how scientists understood the Great Attractor. They used a technique based on peculiar velocities, the same basic tool the Seven Samurai had used decades earlier, but applied to a much larger and more precise dataset. Instead of just measuring where galaxies were flowing, they traced the flow lines. They mapped, in 3 dimensions, the pattern of galactic motion across an enormous volume of space. And what they found was that all these flow lines, these paths that galaxies were traveling under the influence of gravity, converged on a single basin of attraction. Not just the Milky Way and its nearby neighbors, not just a few hundred galaxies in our local cluster, 100,000 galaxies, all of them flowing on timescales of billions of years toward the same gravitational heart. Tully and his team defined this enormous structure and gave it a name drawn from Hawaiian, the language of the islands where their observatory sat. They called it Laniakea. In Hawaiian, the word means immense heaven or open skies. Laniakea is a supercluster, the largest structure to which the Milky Way can be said to belong. It spans roughly 500 million light-years from edge to edge. It contains the mass of 100 million billion suns. It encompasses our galaxy, the Virgo cluster, the Hydra-Centaurus supercluster, and tens of thousands of other galaxies, all of them flowing slowly and inexorably toward the gravitational center that Tully's team identified. That center, that gravitational heart of Laniakea, is the Great Attractor. The mystery had not been solved, but it had been reframed. The Great Attractor was not a single strange object. It was the center of a structure we had been living inside without knowing it. The way you might live your whole life inside a country and never understand its borders because you had never seen it from above. We had never seen Laniakea from above. We were inside it. We were part of it. And we were, along with 100,000 other galaxies, slowly falling toward its heart. Let's stop here for a moment and let that settle. You are on a planet that orbits a star. That star is one of 400 billion in the Milky Way galaxy. The Milky Way is one of approximately 50 galaxies in the local group, our immediate galactic neighborhood, bound together by our mutual gravity, stretching about 10 million light-years across. The local group is falling toward the Virgo cluster, a massive collection of more than 1,000 galaxies about 50 million light-years away. The Virgo cluster is itself falling toward the Great Attractor, the gravitational heart of Laniakea, about 250 million light-years away. And Laniakea, this structure that contains 100,000 galaxies and spans 500 million light-years, may itself be falling toward something even larger. The layers of scale here are almost impossible to hold in the mind. The universe is not just big. It is structured in a way that makes bigness feel inadequate as a description. Each layer of structure contains the previous layers the way a set of nested spheres might, each one enormously larger than the last, each one governed by the same force, gravity, operating across distances and timescales that dwarf anything in ordinary human experience. And somewhere in the direction of the constellation Centaurus, hidden for decades behind the dust of our own galaxy, sits the point toward which this entire cascade of matter is falling. It is not a point, really. It is a region, a concentration, a basin of gravitational attraction that has been shaping the flow of matter across a significant fraction of the observable universe for longer than the Earth has existed. And it is not the end of the story, not even close, because there is something else out there, something even larger, even more distant that may be pulling on Laniakea itself. In the 1930s, an astronomer named Harlow Shapley was cataloging galaxies when he noticed something unusual in the direction of the constellation Centaurus. There was a remarkable concentration of galaxies there, a dense, extended cloud of them, far more clustered than the surrounding regions of sky. He noted it, He cataloged it. And then the field moved on because in the 1930s, the tools to understand what he was looking at did not yet exist. What Shapley had found was what we now call the Shapley supercluster, or more precisely, the Shapley concentration. It sits roughly 650 million light-years away from us, far beyond the Great Attractor, far beyond even the boundaries of Laniakea. And it is, by any measure, one of the most massive structures in the nearby universe. The Shapley concentration contains dozens of galaxy clusters. Its total mass is estimated at something like 10 million billion solar masses, an order of magnitude more massive than Laniakea. It is, in our cosmic neighborhood, the largest nearby concentration of matter astronomers have identified. And it turns out that the Shapley concentration is not just sitting out there, distant and irrelevant. It is pulling on us too. For years, the relative contributions of the Great Attractor and the Shapley concentration to our peculiar velocity were debated. Was our motion toward Centaurus caused primarily by the Great Attractor, or was Shapley, further away but enormously more massive, contributing significantly? The answer that emerged from increasingly precise surveys was both. The Great Attractor dominates our local motion, but the Shapley concentration is a significant secondary influence, its enormous gravity reaching across the 650 million light-years between us and drawing our entire supercluster Laniakea and all in its direction. And in 2024, a team of astronomers published a paper suggesting something even more striking. Laniakea itself may not be the largest structure to which we belong. Using the most detailed map of galaxy motions ever assembled, the Cosmic Flows 4 catalog, which tracks the positions and velocities of tens of thousands of galaxies across a volume of space enormously larger than previous surveys. Astronomers traced the flow lines extending beyond Laniakea's borders. What they found was that the flow does not stop at Laniakea's edge. Continues. Laniakea may itself be a subbasin within a larger basin of attraction. A structure centered not on the Great Attractor but on the Shapley concentration, encompassing a volume roughly 10 times larger than Laniakea. If this is confirmed, and it has not yet been definitively confirmed because the surveys needed to fully map structures at this scale are still being built, then Laniakea is to this larger structure what the local group is to Laniakea. A tributary, a piece of something far grander that we are only beginning to perceive. The universe keeps getting bigger every time we build a better tool. There is something philosophically dizzying about this cascade of structure. Consider what it means for the concept of home. You live in a house, on a street, in a city, in a country, on a continent, on a planet, in a solar system, in a galaxy cluster, in a supercluster. Each of these is a level of organization, a context, a frame, and each one is genuinely your home in the sense that you are part of it, you move with it, you are gravitationally bound to its dynamics. Most people, most of the time, think of home as the first few items on that list. The house, the city, maybe the country, the planet in a poetic sense. But you are also home in Laniakea. You are one of the 100,000 galaxies. Well, you are in one of the 100,000 galaxies that are part of this structure, flowing with it, participating in its dynamics, connected to its center by the invisible thread of gravity that reaches across 250 million light-years and tugs, gently but relentlessly, on everything in its basin. And if the 2024 results hold up, if Laniakea is itself part of a larger structure centered on Shapley, then your home is even larger than that. 10 times larger. A structure so vast that no survey has yet mapped its full extent. At what scale does home stop being home? There is no obvious answer. The gravity does not care about the answer. Continues regardless. Let's go deeper into the physics of why something like the Great Attractor exists at all. Because it did not always exist. Nothing in the universe always existed except perhaps the universe itself, and even that is a statement loaded with uncertainty. In the very early universe, the first fractions of a second, the first minutes, the first hundreds of thousands of years, the distribution of matter was almost perfectly uniform. Almost. Not perfectly. The key word. Quantum fluctuations in the earliest instance of cosmic history created tiny variations in density. Regions that were infinitesimally denser than average, and regions that were infinitesimally less dense. The differences were tiny. 1 part in 100,000, an almost invisible ripple in an otherwise smooth sea. But gravity is patient. Over hundreds of millions of years, those tiny overdense regions attracted slightly more matter than their surroundings. Slightly denser regions grew denser still. Matter flowed from underdense regions toward overdense ones. The small became smaller, the large became larger. The initial ripples amplified into the great structures of the cosmic web. Filaments of dark matter formed first, providing the gravitational scaffolding. Ordinary matter fell into the potential wells created by dark matter halos, compressed, heated, and eventually ignited as stars inside the first galaxies. Over billions of years, those galaxies merged, and clusters grew, and superclusters assembled, all driven by the original tiny fluctuations that quantum mechanics wrote into the fabric of the universe in its first moments. The Great Attractor, the gravitational heart of Laniakea, is the end product of this process on an enormous scale. It is the place where, over billions of years, the flow of matter through our region of the cosmic web has been converging. It is not an anomaly. It is not a mystery in the sense of being inexplicable. It is exactly what the physics of structure formation predicts. Given enough time and enough matter, gravity creates centers. What makes it mysterious is its scale, its hiddenness, the way it was discovered not by seeing it but by reading its influence in the motions of 100,000 galaxies. The way it challenges our intuitions about where we are and how we move through the universe. The physics is clear. The experience of the physics is overwhelming. Here is a number worth sitting with. You are currently moving toward the Great Attractor at approximately 600 kilometers per second. Not slowly, not gently, 600 kilometers per second. Every second, you are 600 kilometers closer to the gravitational center of Laniakea than you were the second before. Except that you are not getting closer. This is perhaps the strangest part of the whole story. The universe is expanding. Space itself is stretching, carrying galaxies apart from each other at a rate that increases with distance. The further away two things are, the faster the expansion is carrying them apart. And the expansion is accelerating, driven by the mysterious force called dark energy, that's 68% of the universe's energy budget that physicists can neither identify nor explain. The expansion is not just continuing but speeding up. The rate at which distant galaxies are receding from us is increasing over time. This has a dramatic consequence for the Great Attractor. We will never reach it, despite falling toward it at 600 kilometers per second. Despite the pull of its gravity reaching across 250 million light-years to tug on every star in our galaxy. Despite the 100,000 galaxies of Laniakea all flowing in its direction. Despite all of this, we will never arrive. The expansion of space between us and the Great Attractor is carrying the center away faster than our peculiar velocity can close the gap. We are like a swimmer trying to cross a river that is flowing faster than they can swim. The effort is real, the motion is real, the destination is real, but the arrival never comes. We will fall forever and get no closer. The Great Attractor will recede from us as it pulls us, the two motions locked in an eternal balance where gravity loses to dark energy on these cosmic scales. This is one of the more quietly devastating facts in all of cosmology. Understanding the zone of avoidance, the region of sky where our own galaxy blocks the view of what lies beyond, is important to understanding just how difficult it has been to study the Great Attractor. Picture the Milky Way from outside. A disk of stars, gas, and dust, maybe 100,000 light-years across but only a few thousand light-years thick, flat like a plate. From our position inside the disk, looking outward in the plane of the disk means looking through a maximum amount of that dust and gas. The view is almost completely blocked in visible light. The zone covers roughly 20% of the entire sky. Not a small patch, not a corner that can be conveniently ignored. A full belt running all the way around the celestial sphere, hiding everything behind it. The Great Attractor lies behind this belt. This meant that for the first decade after its discovery, astronomers knew something was there primarily because of what the surrounding galaxies were doing, not because they could see the source of the attraction directly. It was like standing in a dark room and knowing there is a large piece of furniture somewhere nearby because you keep bumping into things that were displaced by it, without ever seeing the furniture itself. The first breakthroughs came with radio surveys. Radio waves are not absorbed by the dust in the galactic plane the way visible light is, and surveys using radio telescopes in the 1990s began revealing galaxies in the zone of avoidance that optical telescopes could not see. The Norma cluster became clearly visible in radio maps, sitting there exactly where the peculiar velocity data predicted the center of the attraction should be. Infrared surveys followed, penetrating further and revealing more detail. X-ray observations from space-based telescopes showed the hot gas that fills the space between galaxies in massive clusters, making them light up in X-rays even when invisible in ordinary light. Slowly, the picture assembled itself, not like a photograph being developed, more like a puzzle being built from the outside in, the edges first, the center last, and most difficult. What the assembled picture showed was complex, not a single dominant mass, a region of elevated density, multiple clusters interacting, the Norma cluster at the center, extended filaments of matter connecting to the broader structure of Laniakea, and beyond Laniakea, further out, the enormous mass of the Shapley concentration contributing its gravitational influence to the flow. The Great Attractor was real. Its nature was more diffuse and complicated than early speculations suggested. But it was real. There is a related structure that is almost never discussed alongside the Great Attractor but is necessary to understand the full picture. While the Great Attractor pulls matter toward it, there is also a region in roughly the opposite direction in the sky that appears to be pushing matter away. It is called the dipole repeller. Identified in 2017 by a team including Yehuda Hoffman of the Hebrew University of Jerusalem, the dipole repeller is a vast underdense region, a void sitting roughly in the direction of the constellation Gemini. It does not actually push galaxies away in the sense of exerting a repulsive force. It is simply so empty, so lacking in mass, that its gravitational influence is negligible compared to the regions around it. What this means is that matter flows away from the dipole repeller not because it is being pushed, but because it is not being pulled. It is falling toward everything else, toward the Great Attractor, toward denser regions, and the void is left behind. Think of it this way. Imagine a table with a heavy ball in the center and an empty region at one edge. If you place a marble anywhere on the table, it will roll toward the heavy ball and away from the empty edge, not because the empty edge is pushing it, but because the heavy ball is pulling it and the empty edge offers nothing to compete. This is exactly what is happening on cosmic scales. The dipole repeller is the empty edge. The Great Attractor is the heavy ball. And all the galaxies in between, including ours, are the marbles. The combination of the Great Attractor pulling from one direction and the dipole repeller providing no resistance from the other creates the bulk flow that astronomers have been measuring and trying to explain for 50 years. Our galaxy's motion through space is the result of this tug-of-war between something and nothing. Let's talk about what the Great Attractor is not. This is important because the name is evocative in ways that can mislead. It is not a black hole, not even a supermassive one. The mass of the Great Attractor is distributed across a region of space hundreds of millions of light-years across. No black hole has ever been observed with a mass even remotely approaching the estimates for the Great Attractor's total mass. And the dynamics of how we are moving toward it are completely inconsistent with a black hole scenario. The motion is a slow, distributed gravitational flow, not the sharp infall that characterizes regions near black holes. It is not a single galaxy, not even the most massive galaxy ever observed. Galaxies, even the most enormous ones, the brightest cluster galaxies that sit at the centers of massive galaxy clusters, have masses in the range of trillions of solar masses. The Great Attractor has a mass of something like 10,000 trillion solar masses. Thousands of the most massive galaxies ever observed, plus the dark matter halos around them, plus all the hot gas between them. It is not evidence of something supernatural or outside the known laws of physics. The Great Attractor is a natural consequence of gravity acting on the density fluctuations left by the Big Bang. It is unusual in scale, yes, but scale is not mystery. The same physics that governs the fall of an apple governs the flow of 100,000 galaxies toward the gravitational heart of a supercluster. Newton's law of universal gravitation does not have a cutoff. It operates everywhere, at every scale, as long as there is mass. What makes the Great Attractor genuinely mysterious, what makes it deserving of careful thought and quiet wonder, is not that it defies explanation. It is that it forces a reckoning with scale, with the smallness of everything we normally think of as large, with the sheer antiquity and patience of gravity, which has been building the structure for billions of years without any urgency, without any timeline, simply because mass attracts mass and time is available in enormous quantities. The mystery is not physics. The mystery is perspective. Now let's go back to you, lying here in the dark, and think about what all of this means for the most personal question this topic raises. Does any of this matter? Not in the cosmic sense. Not in the sense of whether the Great Attractor cares about you or whether your existence changes anything about the gravitational dynamics of Laniakea. Of course not. You are one person on one planet orbiting one star among 400 billion in one galaxy among 100,000 in a supercluster that is itself one piece of a cosmic web containing more than 1 trillion galaxies. The scale difference between you and the Great Attractor is so enormous that the word enormous becomes a kind of joke. But there is a different way to ask whether it matters. It matters in the sense that it is true. You are right now part of this, not metaphorically, not poetically, physically, gravitationally, materially part of the flow of matter through Laniakea toward the Great Attractor. The atoms in your body, borrowed from the universe for the duration of your life, are participating in the dynamics of the largest structure in your cosmic neighborhood. You are part of something that has been assembling itself since the universe was a fraction of its current age. You are a temporary arrangement of matter in a flow that has been running for billions of years and will continue for billions more. The fact that you are too small to perceive your own motion in this flow does not make the motion less real. The fact that the timescales involved are incomprehensible to a human lifetime does not make the structure less present. You are, in the most literal physical sense, being pulled toward the Great Attractor right now. And so is every person who has ever lived, every person alive today, and every person who will be born in the future, as long as the human species exists on this planet. We are all, every one of us, falling. The discovery of dark matter is inseparable from the story of the Great Attractor, because dark matter is what makes the Great Attractor possible. The mass estimates for the Great Attractor, 10 to the 16 solar masses roughly, could not be accounted for by ordinary matter alone. The galaxies visible in the region, the gas detected in X-ray surveys, the stars and dust and everything that emits or absorbs radiation, all of this adds up to far less than the mass implied by the peculiar velocities. Most of the Great Attractor's mass is dark matter. This is not surprising because most of the mass of the universe is dark matter. The ordinary matter, the atoms, the stars, the gas clouds, the galaxies themselves, is about 5% of the total energy budget of the universe. Dark matter is about 27%, 5 times more abundant, surrounding every galaxy in enormous halos, filling the filaments of the cosmic web, providing the gravitational skeleton on which ordinary matter is draped. In the case of the Great Attractor, the dark matter halo around this entire region, encompassing the Norma cluster and all the galaxy clusters that contribute to the concentration, is vastly more massive than the ordinary matter it contains. What we see with our telescopes is the decoration. The real mass, the thing actually doing the gravitational work of pulling 100,000 galaxies across hundreds of millions of light years, is invisible. This is always the answer when the math doesn't add up. When the visible mass is insufficient to explain the observed dynamics. When the galaxies rotate too fast, when the clusters move too energetically, when the peculiar velocities are too large. The answer is always more dark matter. And yet we have never directly detected a dark matter particle. Not in 50 years of searching. Not with the most sensitive detectors ever built. Not in underground laboratories shielded from every other known particle. Not in colliders smashing protons together at energies that recreate conditions from fractions of a second after the Big Bang. The Great Attractor is mostly made of something we cannot see, cannot touch, and cannot directly detect. We know it is there because of what it does. That is, in a very real sense, all we know. Let's think about the Norma cluster specifically, because it is the visible heart of the Great Attractor, the most obvious concentration of ordinary matter at the gravitational center of the region. The Norma cluster, also known as Abell 3627, sits about 220 million light-years away, almost exactly behind the galactic plane of the Milky Way. It is a rich cluster, one of the more massive in the nearby universe. It contains thousands of galaxies, enormous quantities of hot gas between them, and a dark matter halo of staggering proportions. When X-ray observatories finally mapped it clearly, it revealed itself as exactly the kind of structure astronomers expected at the Great Attractor Center. A massive, concentrated, dynamically active cluster with all the signatures of ongoing galaxy mergers and gas accretion that characterize the most massive structures in the universe. But it was not alone. Surrounding the Norma cluster, in the same general region of sky, were other clusters, the Centaurus cluster, the Hydra cluster, further concentrations of mass that together form what is sometimes called the Hydra-Centaurus supercluster. The Great Attractor is not one cluster. It is an entire region of elevated mass density, a gravitational basin whose center happens to lie in the Norma cluster's neighborhood. And all of it, the Norma cluster, the Hydra-Centaurus concentrations, the dark matter halos surrounding them, the hot gas filling the space between the galaxies, is, by cosmic standards, reasonably close to us. 200 to 300 million light-years. In a universe 13.8 billion light-years in radius, this is practically next door. The most powerful gravitational influence in our cosmic neighborhood, the thing shaping the flow of matter across a volume containing 100,000 galaxies, is right nearby. On cosmic scales, here is something that is easy to overlook when thinking about the Great Attractor. We are not just observers of this process. We are participants in it. The Milky Way's gravity contributes, however infinitesimally, to the overall gravitational dynamics of Laniakea. Everything that has mass contributes. Every galaxy in the local group, every star in every one of those galaxies, every planet, every asteroid, every cloud of gas, every dark matter particle in our halo, all of it adds to the gravitational sum. Your body, negligible as it is on these scales, is part of the mass of the Milky Way. Your atoms are part of what the galaxy brings to its gravitational contribution to Laniakea's dynamics. This is not meaningful in any practical sense. The mass of a human body is so incomprehensibly small compared to the mass of a galaxy that no calculation including or excluding it would produce a different result to any number of decimal places that matter. But it is true, and there is something about its truth worth acknowledging. The universe is not divided into the cosmic and the personal. They are the same thing operating at different scales. The Great Attractor and the atoms in your body are both expressions of the same physics, the same fundamental forces, the same universe assembling itself according to the same rules. The scale difference is real. The separation is not. There is a question that the Great Attractor raises that is rarely asked directly. What happens when we get there? The universe is expanding. The Great Attractor is receding. We will never reach it. This we have established. But let's set aside the expansion for a moment and ask the question anyway. What would it mean, in principle, for the galaxies of Laniakea to fall all the way to the gravitational center? The answer, on long enough timescales, is a massive merger. The galaxies that make up Laniakea are falling toward the center along the filaments of dark matter that thread the supercluster. If the expansion were not carrying the center away, they would eventually fall in, cluster together, merge into increasingly massive structures. This is actually what happens on smaller scales and has been happening throughout the history of the universe. The Milky Way and Andromeda, our nearest large galactic neighbor, about 2.5 million light-years away, are on a collision course. In about 4 to 5 billion years, they will merge. The merger will not destroy the stars in either galaxy. The stars are too small relative to the distances between them for direct stellar collisions to be common. Instead, the two galaxies will interpenetrate, their dark matter halos merging first, then the stellar populations mixing and being flung into new orbits by the gravitational dynamics of the encounter. Eventually, they will settle into a single, larger elliptical galaxy, a combined structure that astronomers have already nicknamed Milkometa. This process, galaxy mergers, is not rare. It is the dominant mode of galaxy growth across cosmic history. The largest galaxies in the universe today got large by consuming smaller ones. The most massive galaxy clusters got massive by accreting smaller clusters. The Great Attractor represents this process at supercluster scale, a gravitational center toward which matter has been flowing for billions of years, assembling the most massive structure in our cosmic neighborhood from the tributaries of smaller concentrations. We are part of a merger happening in slow motion on a scale too enormous to perceive from inside it. The year 2014, when the Laniakea paper was published, was a watershed moment in the study of the Great Attractor. But the story has continued since then, and the most recent developments are perhaps the most striking. The Cosmic Flow Surveys, a series of increasingly precise catalogs of galaxy distances and peculiar velocities assembled by Brent Tully's group and collaborators, have extended the mapping of the local flow field to greater distances and with greater precision than ever before. Cosmic Flows 4, published in 2022, contained measurements for tens of thousands of galaxies across an enormous volume of space. These surveys have revealed something important. The flow field is more complex than the simple picture of everything flowing toward the Great Attractor suggests. There are subbasins within Laniakea. Galaxies in different regions flow toward different local attractors before joining the larger flow toward the Great Attractor. The structure is hierarchical, structures within structures, flows within flows, a fractal complexity of gravitational dynamics that simple descriptions cannot capture. The 2024 paper suggesting Laniakea might be a subbasin within a larger structure centered on Shapley was built on this increasingly detailed flow field data. The argument was that the flow lines, when traced far enough beyond Laniakea's nominally defined boundaries, do not diverge but continue, suggesting that the gravitational basin of attraction is larger than Laniakea's formal definition implies. This is not yet a consensus result. Other researchers have argued that the basin definitions depend on how you draw the boundaries, and that Laniakea is still a meaningful structure even if something larger exists beyond it. The debate is ongoing. What is not debated is the direction. The data consistently point toward Shapley. The flow is real. The question is only where the boundary of our gravitational home is drawn. And boundaries in cosmology are always provisional. Let's spend some time on the Shapley concentration itself, because it deserves more attention than it usually receives. Harlow Shapley, who first noticed the concentration in the 1930s, was one of the great astronomers of the early 20th century, the man who first correctly estimated the size of the Milky Way and our position within it, well off-center rather than at the core as had previously been assumed. His discovery of the concentration that now bears his name was a footnote in a career full of major contributions, and it took decades for its significance to be appreciated. The Shapley concentration sits in the direction of the constellation Centaurus, roughly 650 million light-years away. It contains some of the richest galaxy clusters known, including Able 3558, Able 3559, Able 3562, and a dozen others, all interconnected by filaments of galaxies and hot gas. Its total mass, depending on how far out you define its boundaries, is estimated at somewhere between 10 and 30 times the mass of Laniakea. In the local universe, within a few billion light-years of us, the Shapley concentration is among the most massive things that exists, and it has been affecting our motion for the entire history of the solar system. Long before the first life appeared on Earth, long before the Earth itself formed, long before the solar system assembled from its nebula, the Shapley concentration has been contributing its gravitational pull to the peculiar velocity of whatever galaxy occupies this region of the cosmic web. Our solar system is 4.5 billion years old. The universe is 13.8 billion years old. For the entire history of our solar system, for every year that life has been evolving on this planet, for every species that has lived and gone extinct, for every mountain range that has risen and eroded, for every ocean that has formed and dried, we have been moving quietly and relentlessly under the gravitational influence of the Shapley concentration. Unnoticed, unknown, unexplored, until 50 years ago. There is something profoundly humbling about the fact that we live inside the largest structure in our cosmic neighborhood without knowing it. For the entire history of human civilization, for all of recorded history, for the 10,000 years of agriculture in cities and writing and science, the Milky Way has been part of Laniakea, flowing toward the Great Attractor, influenced by the Shapley concentration. And humans had no idea, not because they weren't looking. The night sky has been studied carefully for thousands of years. Ancient astronomers mapped the stars with extraordinary precision using nothing but their eyes. Medieval scholars built elaborate cosmological models. Galileo turned a telescope to the sky in 1609 and changed everything. But the Great Attractor was simply invisible to all of these efforts. Not just because of the zone of avoidance, though that certainly helped hide it, but because understanding it required being able to measure the velocities of thousands of galaxies, calculate the component of those velocities not explained by cosmic expansion, and identify the systematic flow that reveals the underlying gravitational structure. This required radio telescopes. It required spectroscopy of distant galaxies. It required computers capable of processing enormous datasets. It required the development of the cosmological framework within which peculiar velocities make sense. It required, in short, modern astrophysics, a discipline that did not exist in any recognizable form until the 20th century. For all of human history before that, for 100,000 years of anatomically modern humans, for hundreds of thousands of years of earlier hominids before that, our species looked at the night sky and had no idea that it was being pulled, along with everything else, toward an invisible gravitational heart 250 million light-years away. The sky always looked like the sky. The stars always traced their familiar patterns. Nothing in the appearance of the night sky gave any indication that the entire configuration was in motion, flowing with the slow inevitability of gravity across the most enormous scales imaginable. We found out 50 years ago. In the context of human history, 50 years ago is practically now. The tools that revealed the Great Attractor continue to improve. And as they improve, the picture of our cosmic neighborhood continues to deepen and complicate. The Square Kilometer Array, a network of radio telescopes that will be the largest and most sensitive radio observatory ever built, distributed across sites in South Africa and Australia, is currently under construction. When completed, it will be able to see through the zone of avoidance with unprecedented clarity, mapping the galaxies hidden behind the Milky Way's dust with a precision that previous surveys could not approach. Whatever is hiding in that zone, whatever mass concentrations and galaxy clusters remain to be identified in the most obscured regions of sky, the Square Kilometer Array will reveal them. The final pieces of the Great Attractor's environment, hidden from view for decades, will become visible. The next generation of galaxy surveys, projects like the Dark Energy Spectroscopic Instrument and the Rubin Observatory's Legacy Survey of Space and Time, will extend the precise mapping of galaxy positions and velocities to distances and completeness that dwarf current catalogs. The Cosmic Flows series will continue, growing more comprehensive with each iteration. The flow field will be mapped with increasing precision, and the question of whether Laniakea is a subbasin of something larger will be answerable with data rather than inference. The James Webb Space Telescope, now operating in its 4th year, continues to reveal the early universe with unprecedented clarity. While Webb's primary domain is the distant early universe rather than the local large-scale structure, its observations of early galaxy formation are directly relevant to understanding how structures like the Great Attractor assembled, how the fluctuations of the early universe gave rise to the concentrations of matter we see today. The story of the Great Attractor is not finished. It has barely begun. Let's go back to the beginning, to the very beginning, because the Great Attractor did not appear from nowhere. Its existence was written into the universe from its first moments, encoded in the quantum fluctuations of the primordial energy field, stretched to cosmic scales by inflation, amplified over billions of years by gravity. The region of space that is now the Great Attractor was 13.8 billion years ago, a region of space that was infinitesimally denser than average. 1 part in 100,000 denser than the surrounding universe. A ripple, a barely detectable perturbation in the otherwise smooth distribution of energy in the newborn cosmos. That ripple was enough. Gravity is patient. It has no deadline, no urgency, no impatience with slow processes. It simply pulls everything with mass toward everything else with mass, always, continuously, without pause or interruption. Over the first billion years of the universe's history, that initial overdensity attracted more matter from its surroundings. As it grew denser, its gravitational pull grew stronger, attracting still more matter. The process fed back on itself, slowly but inexorably. Denser regions got denser. Less dense regions lost matter to denser neighbors and became voids. The cosmic web assembled itself across billions of years, not from any external design or purpose, but from the mathematics of gravity operating on the initial conditions set by inflation and quantum mechanics. The Great Attractor is what that process looks like in our region of the universe, integrated over almost 14 billion years. It is the universe doing what the universe does, gravity assembling matter into structures, structures into larger structures, flowing toward equilibrium on timescales that make geological time look instantaneous. We happen to live inside one of those structures. We happen to be part of one of those flows. We happen to be the first species in the 13.8 billion year history of this process to have noticed what is happening and built the mathematics and instruments to understand it. There is something worth saying about the zone of avoidance that goes beyond its role as an obstacle to observation. The fact that our own galaxy blocks our view of the Great Attractor, the most powerful gravitational influence in our cosmic neighborhood, is a kind of cosmic irony that feels almost deliberate, though of course it is not. We are inside the very structure that most complicates our ability to study our cosmic context. The Milky Way, our home, the thing we are most immediately and intimately part of, is also the thing that hides from us the largest structure we belong to. This situation has a resonance with other cases in science where the observer's position fundamentally shapes what can be observed. We cannot see the full structure of the Milky Way from inside it, for the same reason that you cannot see the shape of a forest while standing in the middle of it. We cannot directly observe the most massive structure in our local universe because our own galaxy sits in the way. The universe does not arrange itself for our convenience. It does not clear the view. It does not make the most important things the most visible. Sometimes the most important things are the hardest to see, hidden not behind any barrier we could remove, but behind ourselves. The astronomers who eventually understood the Great Attractor did so not by seeing through the obstruction but by reading the evidence on the other side, the motions of galaxies across the sky, the systematic flow that implied something unseen at its source. They worked backward from effects to cause. From the behavior of matter they could see to the distribution of mass they could not. This is, in a sense, how most of the important work of science is done. Not by looking directly at the thing, but by understanding what the thing does to everything around it. Let's talk about where we are falling from, as well as where we are falling to. While the Great Attractor pulls us from one direction and the dipole repeller offers no resistance from the other, there is also the question of the local dynamics, the smaller-scale gravitational environment in our more immediate neighborhood. The Virgo cluster, about 50 million light-years away in the direction of the constellation Virgo, is the dominant mass in our local supercluster. It is not as massive as the Great Attractor region, but it is much closer, and proximity matters in gravity. The Milky Way, along with the rest of the local group, is falling toward the Virgo cluster at roughly 250 kilometers per second, superimposed on the larger scale flow toward the Great Attractor. This is typical of the hierarchical structure of the flow field. At the smallest scale, galaxies fall into clusters. At a larger scale, clusters fall toward superclusters. At the largest scale, superclusters flow toward the most massive concentrations in their region of the cosmic web. Each scale of motion is real. Each is occurring simultaneously. The Milky Way is doing all of these things at once, falling toward the Virgo cluster while flowing with the local group toward the Great Attractor while being influenced by the Shapley concentration and the dipole repeller and the overall expansion of the universe. The result is our peculiar velocity, our net motion through space after subtracting the cosmic expansion. It points roughly in the direction of the Great Attractor because on the scales of our local flow field, that is the dominant gravitational influence. But it is the sum of many contributions operating simultaneously at many scales. There is no direction in the universe that we are simply drifting. Everything pulls on everything. We are always falling somewhere. The concept of a basin of attraction, the tool that Tully's team used to define Laniakea, is worth understanding more deeply because it reveals something important about how cosmologists think about structure. A basin of attraction, in this context, is defined by the flow of galaxies. If you trace the peculiar velocity of a galaxy, the direction and speed of its motion through space after removing the cosmic expansion, and you follow it forward in time until it either flows into another basin or converges on a center, you have mapped one flow line. Do this for every galaxy in a region and you have the full flow field. The basin of attraction is the region where all the flow lines converge on the same center. It is the cosmic equivalent of a watershed, the region where all the water, however far it travels, eventually flows to the same river and then the same ocean. Laniakea is defined as the watershed of the Great Attractor. All the galaxies within Laniakea are flowing, eventually, toward the same gravitational center. The boundary of Laniakea is the dividing ridge, the cosmic continental divide, where flow lines going one way join Laniakea and flow lines going the other way join a neighboring structure. This is a beautiful and natural way to define a supercluster, not by some arbitrary density threshold, but by the actual dynamics of how matter moves. It captures something real about the gravitational structure of the universe. And it is a definition that can be refined as the data improves. As peculiar velocity surveys become more precise, the boundaries of Laniakea and the boundaries of any neighboring structure that might contain it can be drawn more accurately. The 2024 suggestion that Laniakea is a subbasin of a larger structure centered on Shapley is, in these terms, a claim about where the true continental divide lies. If the flow lines that are currently attributed to Laniakea actually extend beyond Laniakea's defined boundaries and converge eventually on Shapley rather than diverging toward neighboring superclusters, then Laniakea is not the top level of the hierarchy. It is a subbasin, and the true basin is 10 times larger. The answer to this question requires data from surveys that do not yet fully exist. The answer is coming, but it is not yet here. It is worth pausing to consider the extraordinary intellectual achievement that the discovery and understanding of the Great Attractor represents. The human beings who discovered it, the 7 samurai and their contemporaries, had no direct way to see it. They had data on galaxy distances and velocities. They had mathematics. They had the framework of general relativity and the Big Bang cosmology within which peculiar velocities could be interpreted. And from these indirect clues, they inferred the existence of an enormous concentration of mass, hidden behind our own galaxy, 250 million light-years away, exerting a gravitational influence on 100,000 galaxies across hundreds of millions of light-years. This is not different in its logical structure from the detective work of inferring a crime from evidence rather than witnessing. You work backward from what you can observe to what must have caused it. You build the simplest and most consistent explanation for all the clues. You remain open to revision as new evidence arrives. The scientists who did this work were not using exotic instruments or revolutionary new physics. They were using basic principles, the Doppler shift, Newtonian gravity, the Hubble law of cosmic expansion, and careful, painstaking measurement of large numbers of galaxies. The result was the discovery of one of the largest known structures in the universe, hidden in plain sight, expressed only in the motion of the matter around it. It is one of the more extraordinary detective stories in the history of science. Now, as you lie here, I want to give you a sense of what the Great Attractor would look like if you could somehow travel to it and see it from close range. You would see a rich cluster of galaxies, the Norma cluster at the center, thousands of galaxies packed into a volume of space a few million light-years across. The largest galaxies in the cluster, the ones that have grown fat by consuming their neighbors over billions of years, would be enormous elliptical galaxies, featureless, reddish, ancient, containing hundreds of billions of stars but none of the active star formation that characterizes younger spiral galaxies like our own. between the galaxies, filling the space that looks empty but is not, would be an enormous cloud of hot gas. The intracluster medium, heated to tens of millions of degrees by the energy released as matter falls into the cluster's gravitational well. This gas would be invisible to your eyes. It emits primarily in X-rays, but to an X-ray detector, it would outshine everything else. A glowing halo of superheated plasma surrounding the cluster and extending far beyond the outermost galaxies. And everywhere, invisible, would be dark matter. The halo of dark matter surrounding the Norma cluster is many times larger than the cluster itself in visible light. It extends far beyond the outermost galaxies, gradually merging with the dark matter halos of neighboring clusters in the complex, interconnected web that is the Great Attractor region. If you could somehow trace the dark matter, see it directly, which we cannot, you would see filaments of it extending in all directions from the cluster center, threading through the space between galaxies, connecting the Norma cluster to the rest of the Laniakea structure, to the broader Shapley concentration beyond. The visible galaxies are points of light on an invisible scaffold. The real architecture is dark. This is, in miniature, the story of the whole universe. There is one more layer to this story that deserves telling, and it is perhaps the most humbling of all. The Great Attractor, the Laniakea supercluster, is, by cosmic standards, small. Not small in any human sense. Not small in any planetary or stellar or even galactic sense. But in the context of the full observable universe, Laniakea is one of many comparable structures. The Sloan Great Wall, discovered in 2003, is a filament of galaxies stretching approximately 1.37 billion light-years, more than twice the diameter of Laniakea. The Hercules Corona Borealis Great Wall, identified in 2014, stretches nearly 10 billion light-years, approaching a significant fraction of the radius of the observable universe. These structures may push against or violate the cosmological principle, the assumption that the universe is, on sufficiently large scales, uniform in all directions. If structures as large as the Hercules Corona Borealis Great Wall are real, they exist on scales where the universe should be homogeneous, and their existence challenges the standard cosmological models. The debate about whether these enormous structures are real, or whether they are statistical flukes in sparse surveys that do not yet sample the universe evenly enough to distinguish real structure from noise, is ongoing. But they point toward something important. We may not have seen the largest structures that exist. We may not have mapped the full hierarchy. Laniakea may be a piece of something larger, which may be a piece of something larger still, all the way up to scales where the expansion of the universe finally erases structure and everything becomes smooth. Or the universe may have structure on scales we have not yet imagined, larger than anything we have surveyed, defying the expectations of our current models. We do not know, and the honest answer to this not knowing is not frustration. It is wonder. Here, then, is the full picture as best we can draw it. You are on a planet orbiting a star in a galaxy cluster called the Local Group, in a supercluster called Laniakea, in a cosmic web that spans the observable universe. At the heart of Laniakea is the Great Attractor, a region of elevated mass density, dominated by the Norma cluster and its neighbors, hidden for decades behind the dust of our own galaxy. Its total mass is approximately 10,000 trillion solar masses, the vast majority of it invisible dark matter. Everything in Laniakea, every galaxy, every cluster, every isolated star and gas cloud, is flowing toward this center at hundreds of kilometers per second. Including us, including you, we will never arrive, because the accelerating expansion of the universe is carrying the center away faster than our motion can close the gap. Beyond Laniakea, 650 million light-years away, the Shapley concentration, one of the most massive structures in the nearby universe, exerts its own gravitational influence on our motion. And it may be that Laniakea is not the largest structure to which we belong, but only a piece of a larger gravitational basin centered on Shapley. This entire situation, the flow, the structure, the hidden attractor, the dipole repeller providing no resistance from the other side, was completely unknown to science until 50 years ago. We live inside the largest structure in our cosmic neighborhood and discovered it within living memory. The universe is old. Our understanding of it is new. The night is quiet now. The motions are too slow and too vast to feel. The pull of the Great Attractor does not announce itself. The flow of Laniakea leaves no sensation in the body, no pressure on the skin, no whisper in the ear. You are falling, and the fall is silent. This is how the universe mostly works. Its largest processes are the ones most completely invisible to direct experience. The formation of galaxy clusters, the flow of matter along dark matter filaments, the slow assembly over billions of years of the largest structures that have ever existed. All of it happening in silence, at speeds that are extraordinary by human standards but glacial by cosmic ones, across distances that no unit of human experience can make intuitive. And yet it is real, more real in a sense than most of what fills ordinary waking hours. The Great Attractor was there before there was anyone to notice it. It will be there, or rather, it will have evolved into something different, shaped by the continued expansion and the continued fall of matter, long after everyone now alive is gone. It is indifferent to us, not because indifference is a quality it possesses, but because indifference implies the capacity for attention that was instead withheld. The Great Attractor has no attention to withhold. It is mass and gravity and the mathematics of general relativity, operating across scales that make the distinction between your life and its absence irrelevant. And yet, you are the part of this that knows it is happening. The Great Attractor pulls on the atoms in your body with exactly the same force it pulls on the atoms in a rock on the moon, or a gas cloud in the Virgo cluster, or a star in the Norma cluster at its very center. The force is the force. The mathematics do not distinguish, but you know it. You can hold it in your mind, imperfectly, inadequately, with all the distortion that comes from trying to imagine scales beyond imagination. But you can do it. You can lie here in the dark and think about a gravitational heart 250 million light years away and understand, in some genuine sense, that you are falling toward it. This is what it means to be conscious in a universe this large. Not that it cares about you, it does not, but that you can know it. And knowing it, even briefly, even imperfectly, is the closest thing to touching the scale of the universe that a creature of your size and duration is ever likely to manage. Fall well, sleep well. For those still listening, as the boundary between waking and sleep continues to soften, there is something worth saying about the future of this research, about where our understanding of the Great Attractor and the large-scale structure around it is headed. The next decade will bring surveys of galaxy positions and velocities more comprehensive than anything that exists today. The Rubin Observatory in Chile, now beginning its decade-long survey of the southern sky, will catalog billions of galaxies with precise positions and photometric redshifts. The Dark Energy Spectroscopic Instrument is already operating, building the largest three-dimensional map of galaxies ever made, extending to distances where the large-scale structure of the universe can be studied across cosmic time. These surveys will do something that previous surveys could not. They will map the flow field, the peculiar velocity field, with enough precision and over enough volume to definitively answer whether Laniakea is a subbasin of a larger structure, what the true boundaries of our gravitational home are, and how the Great Attractor's influence compares to the Shapley concentrations across the full range of scales. The zone of avoidance will become less of a barrier. The square-kilometer array, once fully operational, will see through the galactic plane in radio waves with a sensitivity and resolution that will reveal galaxy clusters hidden there in detail comparable to the best optical surveys of unobscured sky. The hidden side of our local universe will finally be fully mapped. And as the mapping improves, the theoretical models will be tested more stringently. The predictions of standard cosmological models about how structure forms, how massive concentrations like the Great Attractor assemble, how the flow field relates to the underlying dark matter distribution, all of these will face more precise observational tests than have previously been possible. Some predictions will be confirmed, others may fail, and the failures, if they come, will point toward whatever is missing from our current picture. This is how science works. Not by building permanent monuments of settled truth, but by building provisional maps that become more detailed and more accurate with each generation of measurement. The Great Attractor has been on the map for 50 years. The map is still being drawn. The Milky Way has been falling toward the Great Attractor for as long as the Milky Way has existed. The Milky Way is approximately 13 billion years old, almost as old as the universe itself. For 13 billion years, through the formation of the first stars, through countless generations of stellar birth and death, through the assembly of the galaxy from smaller pieces, through the formation of the solar system 4.5 billion years ago, through the origin of life on Earth, through the rise and fall of the dinosaurs, through all of recorded human history, the galaxy has been flowing, with everything in it, toward the gravitational heart of Laniakea, and will continue to do so, not arriving, not stopping, just falling in the way that orbiting objects fall, perpetually in motion toward something they never quite reach, the fall and the recession balanced in a dynamic that continues as long as both the gravity and the expansion persist. On timescales of billions of years, the accelerating expansion will eventually dominate completely. The galaxies that are now falling toward the Great Attractor will find themselves carried away by the expansion faster than gravity can pull them back. The large-scale structure that defines Laniakea will begin to unravel. Galaxies that are currently gravitationally bound to each other will eventually be separated by expanding space, losing sight of each other as the universe grows too large for light to cross between them in any reasonable time. The Great Attractor will eventually cease to be an attractor in any meaningful sense for the outermost galaxies of Laniakea. Only those already gravitationally bound, already close enough that their mutual gravity exceeds the pull of dark energy, will remain together. The rest will drift apart into the accelerating expansion, each galaxy cluster becoming its own island universe, surrounded by expanding emptiness, losing connection with everything beyond its own gravitational reach. This is the long future of the universe, not a dramatic end, not a collapse or a crunch, just a slow, gentle, irreversible dispersal. The connections fading, the structure dissolving, the universe becoming more homogeneous again, on longer timescales than the ones that built the structure in the first place. The Great Attractor, in some distant cosmic future, will have accomplished all the gathering it is capable of. The matter within its gravitational reach will have merged into the most massive structures that gravity can assemble before the expansion wins. And then even those structures will cool and darken and fade into the long, cold equilibrium of a universe running down. We are not near that future. We are in the middle of the universe's life, the era of structures and flows and complexity, the era of galaxies and stars and planets and life and consciousness. This is the era of the Great Attractor, and we are here to see it. Sleep well.